Most of the time, I'm not going to actually know what my true population proportion is. Let's say, for example, that I wanted to know what the proportion of people who are left-handed in the United States is. I probably don't know that, but I could probably make a relatively good guess by looking at a small subset, a small sample of people that are representative of the entire population, and calculating the percentage in there that are actually left-handed. Now, that would be one guess, though. If I did this a number of times for different samples, I'd have a bunch of guesses that are all hover around what the true population proportion is. So I'm able to make a better, more informed guess using a range of values, and that's what we mean by a confidence interval. So let's take a look at how to build one. So first of all, if I don't know what the true population proportion is, then I can't make the standard deviation for that population proportion. So I substitute in the standard error instead. It's the exact same formula as my standard deviation, except I'm using the population, instead of using the population parameter, I'm using my sample statistic. So I use the proportion for the statistic, 1 minus the proportion for the statistic over the n in the sample. Square root that, and that's my standard error, which is a substitute for the standard deviation. Then just like we said that that 68% of our data will fall within one standard deviation of the mean or the true proportion, well, the same would be true for the standard error. So 68% of my samples will lie within one standard error of the population proportion, 95 within 2, and 99.7 within 3. So if we look at this statement, we would be sure that about 99.7% sure the true population parameter is within 3 standard errors of whatever the sample proportion we calculated is. That's pretty sure. That's the idea of a confidence interval. It's a range of values, 3 standard deviations below to 3 standard deviations above, in which we are this sure that our true population parameter lies in there. So it's an interval of values fairly certain to contain the true value of the population parameter. The degree of confidence reflects that degree of certainty. What does it mean exactly to say I'm 95% confident? Well, my true population proportion is lying at some fixed value, whatever, let's say it's this green line right here. That's the true population proportion. Every time I draw a random sample and build a confidence interval, it'll give me a range of values surrounding the sample value. If I'm doing 95% confidence, then that means that 95 of the intervals that I build will overlap the green line, the true population proportion, and 5% will miss it. So we could have constructed a confidence interval that completely misses what the true population proportion is. We don't know. There is no certainty here. This is just kind of our best guess, our best estimate of where that actually lies. So from the empirical rule, we know that 95 is about 2 standard deviations. Well, it's going to turn out that it's not exactly 2. I'm going to show you in a minute how to figure out the number that goes here. But we can use 2 as an estimate in our mind to do a mental calculation. If I do 2 times the standard error and add and subtract that to my sample proportion, that would give me a roughly 95% confidence. This guy's called the margin of error, how far away from the sample proportion we're going. In this case, 2 times the standard error. That margin of error is kind of like how much wiggle room we have in our estimate. So another way to write our formula for a confidence interval is our estimate plus or minus the margin of error. If the margin of error is too wide, it's not useful for us. I don't want to cast too wide of a net. I don't want to be too certain that that I'm actually capturing the population parameter, because if I am, then the values that I'm getting are no longer useful. They're not meaningful enough. So I want to do a balancing act between my level of certainty and um, the estimate that I'm making. All right, so that 2 in there, as I said, is just a rough estimate from the empirical rule. It turns out that it's actually 1.96. Now, where do we get that from? Well, if we look at a standard normal curve, the 95% means 0.95 is here in the middle. So that means 5% is on the outsides. Half of 5% over here would be 2.5%, so 0.025, and 2.5% over here. So if I go and look up what z value down here gives me an area here of 0.025, I will see either in the chart or by using my calculator, second distribution, inverse norm, 0.025, mean of 0, standard deviation of 1 since it's z-score. There's the 1.96. Now we're going to be using the positive value, even though that gave me back a negative, in our confidence interval formula. So that z star is the critical value, and that allows me to alter my level of confidence. So if I do the same thing for a 90% confidence interval, 90 goes in the middle, which means 5% on each side over here to make the remaining 10%. So 0.05 and 0.05 is the area over here and here. So when I go to my calculator, we're going to type in the exact same thing, except instead of 0.025, I would have 0.05 for the area. And we see 1.645, the z that we saw here. So then our confidence interval formula is our sample proportion plus or minus the critical z value times the standard error. That's just the formula from before. Do not suggest that the parameter varies. The number, the percentage of people in America that are left-handed is whatever it is. It's a fixed value. It doesn't move around. But my uncertainty is on whether I'm actually capturing that with my confidence interval. Remember, if I do a different sample, it'll build a different confidence interval, and I'll have a slightly different estimate. Let's look at an example. So I want to look at number 16 here. First USA is offering their cardholders a campaign. They want to see if enough people will go for it. So out of 50,000 cardholders that they sent the offer to, 1184 registered, we want a 95% confidence interval. So before we begin working the problem, remember the first thing we have to do is check our 3 conditions. First condition is randomization, and it says right here it's a random sample, so we're good there. Now my second condition is no more than 10% of the population. Well, 50,000 cardholders is less than 10% of all cardholders, right? Because if I multiply by 10, right, that would be 500,000. Certainly I have more than 500,000 cardholders. And then my last thing is at least 10 successes and 10 failures. Well, 1184 is bigger than 10, so we're okay there. And 50,000 minus 1184 is bigger than 10, so we're okay there. We've got our 10 successes and failures. All our conditions are met. We can go ahead and build a confidence interval. So, to get the confidence interval, we're going to take our 1184 out of 50,000, 1184 divided by 50,000, and I get 0.02368. So let's say 0.024. That's my p-hat. So the p-hat here is 0.024. I wanted a 95% confidence interval, so that was a critical z of 1.96. My N is 50,000. And then I need the standard error. So to get that, we're going to do the square root of 0.024, 1 minus 0.024, divided by the N, 50,000. All right, let's see what that ends up being. So we're going to go square root of 0.024 times 1 minus 0.024 divided by 50,000. Okay, so remember, that means I've got to move the decimal to the left 4 places. So 3 zeros and then a 684. Okay, so now my confidence interval then is going to be that p hat plus or minus the critical z times the standard error. So that's going to be 0.024 plus or minus 1.96 times 0.000684. So I'm going to go over to my calculator. Oh, whoops. Sorry, I erased it. And we're going to go 0.024 minus 1.96 times our standard error, which we said was 0.000684. And then I'm going to do the same thing. I'm going to do it with a plus sign. So my confidence interval, oh, whoops. Put that plus sign in the wrong place. That should have been 0.024. Try that again. Okay, so we get 0.025, and then the minus was 0.022. So we're fairly certain that the true population parameter lies somewhere between our estimate of 0.0227 and 0.0253. In other words, between 2.5 and 2.6% of cardholders will respond to the offer. Or if our acceptance rate is 2% or less, the campaign won't be worth the expense. Given the confidence interval, should we do it? Yes, because look at our confidence interval. Both of these are greater than 2%. So we're certain at least 2%, or I shouldn't say we're certain. We're 95% confident that at least 2% will respond to the offer. Now, to do this directly on the calculator, you go into the stat key, over to the tests, and look for where it says 1 proportion z test. A z interval, sorry. There we go. 1 proportion z interval, right up here, option A. And our X is the number of respondents that said yes, 1184. Our N is the 50,000. And we wanted a 95% confidence level. And we avoid doing all the math because that's exactly what we did when we did it by hand. All right, we'll pick up with the next example in the next video.